I welcome you all to the A-Level Science Zone. This is General Professor Coletta taking you through the numerical part of applied mathematics. Yes, we are going to look at specifically only 5 topics here, and we are going to use the shortest time possible, but elaborating each and everything very clearly. Allow me say that we are going to begin with the errors. I beg for your attention. Subscribe, share the video. Yes, share the video all in all. Yes, so if you are to begin with the errors in numerical methods, yes, this page ain't very clear, but let's persevere. So they are saying that errors are due to unavoidable inexactness or inaccurate error. Like for example, if you hear the word error, yes, something that is unavoidable, yes, that brings about inexactness or inaccuracy from say measurements, calculations, computations, or even the formula we use. Yes, we find very many errors as we maneuver the subject. Very many people, some people round off. You see, there are very many sources of errors. But now specifically, I want to look at the errors in the numerical what? The numerical methods. The second paragraph, if the accuracy of any measurement is defined as the closeness of the agreement between the experiment value and the true value, which we can call the exact value, then there is some degree of deviation from the exact answer. So the degree of deviation is usually measured in terms of errors. For example, if you had 9.87, when you round off to get 9.9, there is that degree of deviation, yes, of which we can see that from 9.87 to 9.9, you can see that there is a 0.03 absolute error, which we're going to look at in this topic. Yes, then thus in numerical techniques, the magnitude of the error associated with an approximate value can be defined as the exact value minus the approximate value, but we take the magnitude. Yes, so if we are to take the exact, to make the exact value the subject, we shall see that it is equal to the approximate value plus or minus the error. Yes, this will be depending on the accuracy of the measurement instrument. Alright, so we have a note there. Blunders and mistakes from human weaknesses aren't considered to be errors since they can be treated numerically. Yes, those are numerical errors. For example, a very good example is in physics, whereby you see these people doing the practicals. Yes, these people doing the practicals, there are some sources of errors where we say that wind, you see, shaking the table. No, such things. Here we are saying that those errors that are brought to you by you human, can you the person, for example, instead of pressing 2 times 2, you press 2 plus. Those aren't called errors because you can be, you yourself can treat them numerically. We get it? Then we have a subheading under that, notations and symbols. We say if uppercase letters sorry. Yes, that wasn't clear, but I was trying to say that if uppercase letters, for example, capital X, capital Y, capital Z, are used to denote exact quantities, then it implies that the lowercase, then we call the small letters, will, for example, x, small y, small z, will be, yes, to denote the approximate or the esteemed quantity. Yes, therefore, if x denotes the exact value, then x will denote the approximate, the small x. And if we use the small value of x to denote the exact, then the capital will denote the approximate. It means that here we don't need to cram. Please do not cram that capital X will always be the exact or will be the approximate. Please, let's avoid the cram work. Let's just understand the concept behind. Yes, then for example, also if small x is an approximation of capital X, it means from that statement they are saying that Small x is the approximate. They're approximating capital X with the small x. It means that the error in capital X will be denoted. We use we have some things we use to denote the errors. Yes, for example, you can use dx or sigma x or error in what? All those three you are seeing down there are used to denote errors. And the error is also got by subtracting the approximate from the exact. Yes, from that we can see that capital X minus small x, because the statement was small x is an approximation of capital X. It means that capital X was the exact and the small x was the approximate what? The approximate value. Yes, so that is generally the introduction about what? About errors. Yes, I prefer a learner would pause and copy each and every note provided from this video. That's what I beg. Please don't forget to invite your friends that we are learning from this site. Yes, we can have terms used. The first term, we have what we call the absolute error. In general, the maximum absolute error when a number has been rounded off to n decimal places is 0.5 exponent negative n. For example, if a number small x has been rounded off to 3 decimal places, it means that x is equal to, for example, if x is 0.072 and it has been rounded off to those 3 decimal places, then the error, the absolute error, will be 0.5 exponent negative 3. We have said that generally the absolute error is given by 0.5 exponent negative n, where n is the number of decimal places to which it has been rounded off. Now, if we have 0.072 and it has, for example, maybe it was 0.0723 and it was rounded off to 3 decimal places, then the error in that would be gotten by the number of decimal places it was rounded off. For example, that is 0.5 exponent negative 3. The 3 comes about from the number of decimal places it has been rounded off. Yes, in simple terms, to get the absolute error, we just know that it ends with a 5. So you count the number of decimal places. This is the simple way. You count the number of decimal places, and those are the number of the zeros after the point. Then you put a what? A 5. So if it is 0.072, then the error will be 0. Count 3 zeros, 0.0005. That's the simple way we can use that. Then, for example, if it is 0.71, and you want the absolute error will be 0.005. You just count the number of decimal places. Yes, where magnitude of error in x is the maximum absolute error in what? In x. Those notes are very clear there. Then part B there is what we call the relative error. The relative error. Relative error, we just simply get the absolute error over the approximate value. If we don't use the approximate value, we use the working value, because we are simply looking for the relative error. Relative. For example, this I'm sure everyone who is in senior 6, senior 5, you passed through senior 1, and in the beginning there's somewhere we looked at relative density, whereby we say that that's the ratio of the density of a substance to the density of what? Of water. Relative. We are relating the error with something, and simply that is a ratio. So that is what we call the relative error. We shall be using these formulas as time goes on. Then parts, we have what we call the percentage error. So in simple terms, to get the percentage error, we just simply get the relative error times 100. For example, if another example of relative marks, for example, if they are marking out of 80, I can say the relative marks you have, we say your marks relative to what? Again, so you might have gotten 20 out of out of 8. Those are relative marks. Those are your scores. Like, for example, relative to the 80. 20 out of 80. Relative. Yes? Now, if we want to get the percentage, we shall just get those relative scores and we multiply it by 100. Then let's begin with the binary operations of rounding errors using interval arithmetics. We are going to look at the interval arithmetics, then we shall look at the second part of errors. Let's begin with the interval arithmetics we see. Now, the interval arithmetics involves getting the error in an expression by first calculating the maximum value, minimum value, and the working value. After getting these, the error in the given expression will be got from the formula. So if you are to get the absolute error, simply you get the maximum value, you subtract the minimum, then you divide by what? By 2. That's simply how we get the absolute error. That's why I've said that these are binary operations of rounding errors using interval arithmetics. You get the maximum value, you subtract the minimum, then you divide by what? You divide by 2. How do we get the interval? Interval, for example, in trigonometry, they can tell you, find the range of solutions for each sine x blah 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 sine squared plus this is equal to what? And after they say the range given is from 90 degrees to 360 degrees. They can say negative 180 degrees to positive 180 degrees. Any of your choice. But I remind you that the interval here we can only use box bra. Note that we only use box brackets for the error. Yes, then the limits. How do we get the limits? There are two limits. You have what we call the upper limit and the lower limit. The upper limit consists of the maximum value, and the lower limit consists of the minimum value. If we are integrating, we integrate from the lower limit to the upper limit, which is the minimum value to the maximum value. That's why it is very rare you find someone to integrate from 4 to 1. Yes, we integrate from 1 to what? To 2, from A to B, where A is less than B. So those are the different cases. But remember, for the interval, we use box brackets, where we say that minimum value, comma, maximum value. Together, that's the interval. Then we have what we call the relative error. We have already talked about the relative error. Yes, don't mind about those brackets. Then you also have what we call the percentage. The percentage error. Percentage error, we shall use relative error. We multiply it by 100%. Let's dive deeper and see what to solve. Yes, for sure, when you talk about binary operations, what comes into your mind? Here we are looking at how can we get the maximum error and the minimum error in, say, addition, subtraction, multiplication, division, and so on and so forth. Now we want to begin with addition, maximum and minimum value in addition. So let's assume the note you are seeing here, that's just a simple proof of what we are going to talk about. For example, if I have a big number and I add it to a big number, I get a big number, isn't it? If I'm to get a smaller number and a smaller number, I will get a smaller answer compared to the other one, isn't it? Now, if I want the maximum value, if in case we have to just add error, because we have said to get the maximum value, we just get that approximate plus the error, isn't it? Yes, that is how we saw the work in the previous page. Now, here they want to prove that maximum x max plus y max will give us the maximum value. But let's see. They have said that suppose x is 3.22 and y is 2.2 have been rounded off to the given number of decimal places. So what will be the error in x if they have been rounded off? If we say 3.22, meaning that there are 2 decimal places, so the error will be 0.005. And the error in y, since it's 1 decimal place, that is 1 0 after the point, so that is 0.05. So the 4 possible alternatives for adding the 2 values will be as such. We shall have getting x mean and y mean. What do we get? If I are to get the minimum value of x, I'll get the value of x, that given value, and I subtract the error. Plus, how do I get the minimum value of y? I'll get that value of y, I subtract the what? The error. That will be the minimum value of y. So if I'm to add them, I come up with 5.365. Then if I have x mean plus y max, what do I get? I get the minimum value of x by subtracting the error. Then I get the maximum value of y plus adding the error, which is 0.05. You can make that correction on the second calculation. That is 2.2 plus 0.05, not 0.5. That is a simple correction. But when you add, that is the answer you get. Yes, you check, but that is the answer. You get 5.465. Then x max plus y mean, you get 5.375. Then x max plus y max, you get 5.475. Now from the above, we are going to see that 5.36 is the smallest, meaning that x mean plus y mean gives us the minimum value for addition. Then which value is biggest there? We see, but it's 5.47 what? 475, and it is the largest, implying that the maximum value of in addition of x plus y will be got from x max plus y max. In summary, if you are to get the maximum of x plus y, it will be x max plus y max. Then if we are to get the minimum of an addition, we shall say x mean plus y what? Y mean. So what of maximum and minimum value of subtraction? We are following the same procedure, but while subtracting. Let's assume if I get a minimum value and a minimum value and I subtract them, I'll get what we call, it will be minimum, isn't it? But if I get a minimum value and I subtract a maximum, I think I'll get the smallest answer, because on something small, you are removing something big. Yes? But for the first, they say that x mean minus y mean. On that small thing, you remove something small. I think that it won't be the smallest answer. But for x mean minus y max, we get the minimum, the smallest answer for subtraction. Answer internal, Jaco. Small answer minus big answer, you get a smaller answer. So that's what we are trying to do there. So if you are to look through all those, they were just simple proofs to show you that if you get x mean minus y max, you get the smallest answer. Then if you are to get the biggest answer, it will be x max minus y mean for subtraction. So those are simple proofs. Still, they used 3.22 and 2.22 to show you that same thing. Yes, then for multiplication, then if you are to check the summary, from above 0.965 is the smallest, meaning that x mean minus y max will give you the smallest value. Then 1.075 is the largest, meaning that x max minus y mean will give you the maximum value for subtraction. So in summary, the minimum value of x minus y will be got from x mean minus y max. Then the maximum value of x minus y will be x max minus y mean. That's how we can differentiate the two. Then for multiplication, it is the simplest. To get the maximum value of xy, you get x max times y max. The minimum value, x mean times y mean. That's how we simply do that. Yes? Then from those are simple proofs. Yes, I advise you pause and write down, because I believe everything that is shown above is very, very clear and elaborate. I want us to see some worked out examples. Yes, there's this first question from UNEB 2004. It was number 8, paper 2 still. Given that numbers x 2.678 and y 0.8765 measure to the nearest number of decimal places indicated, they said part A state the maximum possible error in x and y. Part B, determine the absolute error in x, y. Then find the limits in which the product x, y lies. Please, you pause and write down the question such that when the video goes on, check the answers. Yes, I believe you are done copying. Start. Then they want the maximum possible error in x and y. How do you get the maximum of x, y? Since it's multiplication, we shall say that is x max times y max. That's why for part A, we first got the errors. Since they were got by rounding off 2.678, there are 3 dp, so the error in x will be 0.0005. Then y is 0.8765, there are 4 dp's, so the error in y is 0. You count 4 zeros, 0.0005. Then to get xy max, it will be x plus error in x times y plus the error in y to get the maximum value of y. Then how do we get minimum of multiplication? Minimum of multiplication will be got from x mean times y mean. That's why on x I subtract the error times on y I also subtract the error. So we saw the formula for getting the absolute error will be maximum minus minimum over 2. That is why I got 0.00572. Then the upper limit will be the maximum value. Then the lower limit will be the minimum value. Just add them, but to the specified number of decimal places. Very simple, like that. Yes, so allow me to give you some sample questions. Please don't cheat yourself. You first try out, then you pause, then you watch, you write down the question, then the answers later on. So that is the first question. You can copy. The length, width and height of a water tank were all rounded off to that 3.65 meters, 2.15 meters and 2.5 meters respectively. Determine in meters cubed the least and greatest amount of water the tank can contain, meaning they want the maximum volume. Very simple. And the minimum volume. Very, very cheap. Yes, please don't cheat yourself. First try out, then the solutions are being brought soon. So if you have those answers, you just tick yourself, because they just wanted the maximum and minimum volume. If it was we know that if when given the length, width and height, that is automatically a cuboid. So volume of a cuboid, that is length times width times height. They were testing the competence of maximum volume, of which we know that volume of a cuboid, someone should be knowing that it's length times width times height. That is getting maximum value in multiplication. To get maximum value in multiplication, that is maximum length times maximum width times maximum height. That's why on each parameter you are adding the error. Then to get the minimum value, we just subtract, we just do the same. Minimum length times minimum width times minimum height. That's why on every parameter they have been subtracting that error. So I want to toss another question. Yes, there is this second question, which I want you to send your solution to my number, the WhatsApp number. Yes, that is 0788953142 for marking free. Yes, that is the number. Copy it and You see what next? Yes, copy the question. The area of a parallelogram formed by vectors is given by area is equal to A magnitude, A tilde magnitude, B tilde magnitude sine theta, where theta is the angle between the vectors. Find the percentage error made in the area. Yeah, everything is very clear. I continue reminding you that this is the exercise I've left. Yes, we shall start from there. We proceed with our errors. Share the video, subscribe, and comment your problem and what else we should tackle. I remain General Professor Koleta. WhatsApp 0788953142 for more. We are still continuing, and I want to show you a recap of what we're going to cover in this lesson.